Welcome to this explainer. Today, we're diving straight into the heavy metal heart of global power generation. We're going to uncover the mechanics of this incredible machine that, quite literally, lights up our modern world. It's this massive piece of engineering that most of us never actually see, yet we rely on it every single time we flip a light switch or plug in our phones.
So let's get right into it, because the underlying reality of our electrical grid is absolutely fascinating. See, regardless of whether your electricity is coming from a burning piece of coal, a jet of combustible gas, or a glowing nuclear rod, it fundamentally boils down to a surprisingly simple concept. We're basically just making really hot water to spin a giant wheel. And believe it or not, that method still generates the vast majority of all global electricity. That giant wheel? Well, that's the steam turbine, literally the ultimate hidden workhorse of modern civilization.
Here is our agenda for today. First, we'll look at the power generation puzzle. Second, decoding the Rankine cycle. And third, the anatomy of a steam turbine.
All right, let's kick things off with Section 1, the power generation puzzle. Now, as we all know, humanity harnesses a really wide variety of fuels to meet our completely endless, ever-growing demand for power. Just look at the sheer diversity of power generation requirements here. We're drawing energy from traditional sources, coal, gas, and oil, right alongside a growing reliance on alternatives like nuclear, wind, solar, geothermal, and biomass. It is this vast, incredibly complex web of primary energy sources, but they're all tasked with the exact same monumental job of powering human progress.
And what's truly awe-inspiring here is the sheer scale of these facilities. Take a towering pulverized coal-fired boiler plant. It operates completely differently than the massive, heavily contained vessels of a nuclear steam supply system. Yet, despite combusting fossil fuels on one hand and utilizing nuclear fission on the other, they serve the exact same foundational purpose. They are generating absolutely incredible amounts of heat to ultimately produce steam. Really, when you think about it, they're just different ways to boil water on a massive industrial scale. So, when engineers are designing these colossal plants, they have to balance some massive competing factors to build a machine that's actually competitive. Because it's not just about making power, right? It's about how efficiently and responsibly we make it. We are constantly optimizing for thermal efficiency to squeeze the absolute most power out of every single ounce of fuel. But obviously that has to be strictly balanced against environmental problems and emissions. Add to that the need for rock-solid reliability, the operating flexibility to actually match grid demand, and of course, the overall costs. It is basically a constant, high-stakes balancing act of thermodynamics, structural mechanics, and economics.
Moving right along to Section 2, decoding the Rankine cycle. To really grasp how a power plant operates, we absolutely have to understand the Rankine cycle. This is the fundamental thermodynamic cycle that acts as the real basis for conventional power generating stations. Honestly, you can think of it like a giant, continuous breathing mechanism for the entire plant. Its sole purpose is to take a heat source, like that giant coal boiler or nuclear reactor we were just talking about, and use it to convert liquid water into extreme, high-pressure steam. So here is exactly how this mechanism works, broken down into 4 basic but super critical steps. First, the water inhales, basically, as it gets pumped to immense pressures. Second, it's heated right up to its corresponding boiling point, going through a phase change from liquid to vapor. Third, we superheat it well above boiling just to pack it with the absolute maximum thermal energy possible. And finally, it exhales. The superpressurized steam expands incredibly fast through a multi-stage turbine to a much lower pressure, exhausting into a condenser to return back to a liquid state so the whole cycle can start all over again. When you look at it in abstract terms, this cycle is just a beautiful, continuous loop of energy transformation. You've got a massive influx of heat energy transferring into a fluid, which is then converted into the kinetic energy required to literally force those heavy turbine blades into rapid motion. And then whatever low-temperature heat is left over just gets exhausted right out.
Which brings us perfectly to Section 3, anatomy of a steam turbine. Now, how do we physically capture all of that invisible thermodynamic energy? Well, inside these machines, you'll find absolute engineering marvels. We're talking about a meticulously arranged sequence of high, intermediate, and low-pressure turbine sections. And these things are designed with mind-blowing precision. They have to withstand extreme, violent pressures and scorching temperatures, all while spinning flawlessly for months or even years on end without a single stop. Just the sheer density of the piping, the massive external casings, and the microscopic alignment of the rotational axis, it's honestly staggering.
Zooming in even closer here, you can clearly see the massive central rotor shaft running right down the middle. That is essentially the spine of the beast coupling to the generator. And surrounding it, you have a really robust protective casing and gland seals. These are basically critical rings that stop the extreme high-pressure steam from just blasting right out of the shaft. But most importantly, check out those meticulously angled turbine blades. They basically act like physical sails, catching the gale force winds of the superheated steam and directly translating all that heat and pressure into raw rotational torque. To really understand how the steam travels through this beast, let's follow the literal steam path. The high-pressure steam comes from the plant's secondary superheater and gets routed right through the main steam line. Now this line splits in two, blasting that extreme steam to two main stop valves. From there, it moves into the external control valve chest, which houses 4 distinct control valves to carefully regulate the flow. Then the steam travels through 4 massive pipes called steam leads. You've got 2 feeding it on the bottom, 2 feeding it on the top, and then finally it violently slams into the main high-pressure turbine, setting the whole system into rapid spinning motion. It is truly a masterclass in fluid dynamics and mechanical engineering. But as we wrap up this explainer, I want to leave you with a bit of a provocative thought. For over a century, the steam turbine has been the undisputed king of power generation, fully optimized for coal, gas, and nuclear heat. But as our global grid shifts more and more toward renewable energy sources, how are these foundational heavy metal engines going to adapt to keep powering our future? Are we going to see them perfectly paired with next-generation geothermal or maybe advanced concentrated solar plants? You know, the fuels we use might completely change, but the elegant physics of just boiling water to spin a giant wheel, well, that just might remain the unsung hero of our modern world. Thanks for joining me today, and keep exploring.